Hello, my name is Richard Shaw from Huawei's Noah's Ark Lab in London, and I'll be presenting our work on HDR image reconstruction from bracketed exposure images and events. High dynamic range imaging methods are used to extend the luminance range beyond what can be captured by a conventional low dynamic range camera. State-of-the-art HDR imaging methods typically involve capturing a sequence of low dynamic range images with different exposure values, also known as exposure bracketing, and then aligning them and merging them with different weights to produce an HDR image. However, HDR methods which combine a sequence of images are restricted by the limited dynamic range per exposure bracket, which can make alignment difficult if there are under or overexposed regions in the images. Furthermore, dynamic scenes can pose a big challenge for HDR imaging methods and can cause unwanted motion artifacts such as ghosting. Event-based cameras are a novel type of sensor that capture motion in a scene by detecting changes in scene brightness. Different from conventional frame-based cameras, they have asynchronous independent pixels which trigger when the brightness change exceeds a certain threshold value. An event is stored at pixel location XY with a timestamp T and event polarity P depending whether the brightness change increased or decreased. If there is no motion in the scene, no events will be detected. This framework enables event cameras to capture visual information at a very high frequency and with a very high dynamic range compared to regular frame-based cameras, making them attractive for the task of HDR reconstruction. Event cameras have been used for HDR image reconstruction before, but these methods are typically limited to low-resolution grayscale images. And because events only provide information in the moving regions, this makes it difficult to reconstruct fine details, particularly in static scenes. State-of-the-art methods are relatively poor quality and suffer from reconstruction and temporal artifacts compared to image-based HDR methods. Therefore, in this work, our idea is to combine the best of both worlds from each input modality: high frequency and high dynamic range information from an event camera, and rich colors and fine details from a sequence of low dynamic range images captured at a lower frequency. We propose a multimodal HDR network architecture, as shown here, which processes each input modality separately before combining their extracted features downstream with a fusion network. Looking at the network diagram, our method is as follows. First, features from 3 input low dynamic range images are extracted using a convolutional neural network encoder, and an attention module is used to suppress misalignments and badly exposed regions in the images. Secondly, the input tone-mapped images are converted to the linear domain using standard gamma correction and are processed with a linear alignment module. This module extracts features from the linearized images using a separate CNN encoder and then uses deformable convolutions to align the features to the middle reference frame. Thirdly, the input event stream is converted to a voxel grid so that it can be processed with a convolutional neural network, and event features are extracted using a separate event encoder. The event features are aligned to the features at the reference timestamp, again using a deformable convolutional alignment module. Fourthly, a novel event-to-image feature distillation module is used to transform event features into the image feature domain and leverage the high-frequency information provided by the events in between the low dynamic range images. Finally, the feature maps from each of the input processing modules are stacked and fused together using an HDR reconstruction backbone consisting of dense residual blocks and outputting the final HDR image. Here, I will explain our novel event-to-image feature distillation module in more detail. The idea of this module is to transform the extracted event features into linear image features, since our end goal is to predict an HDR output in the linear image domain. We apply a self-supervising L2 loss on each of the extracted event features and the linear image features at the corresponding timestamps. The image features are considered as pseudo-labels, and we prevent the gradients from updating these values, encouraging the distillation of event features into image domain features. Because our CNN encoders extract features at multiple scales, we apply this self-supervising loss over each scale and on each of the 3 input low dynamic range images. We are then able to exploit the higher frequency information of the events by using a sliding window over the event stream, to extract intermediate event features in between each of the low dynamic range images, and using the distillation to transform these features into image domain features. Because there are no publicly available datasets containing both bracketed low dynamic range images and event streams, we consider the following two datasets with synthetic and real-world event data to train and evaluate our model. First, we use the HDM HDR video dataset, which consists of ground truth HDR video captured using two ARRI cameras in a mirror rig, for which we generate synthetic events using eSIM, an event camera simulator. And second, for experiments using real-world event data, we make use of DSEC, which is a driving dataset containing simultaneously captured events and low dynamic range video. From these video sequences, we extract well-exposed frames as pseudo ground truth HDR images and degrade these further with a pixel measurement model with noise to produce lower dynamic range input images. Here we present some of our results. We compare our model to a number of different methods which use either only 3 low dynamic range images as input, only events in the case of the method e2vid, and a single low dynamic range image with events in the case of the method neuromorphic HDR. Our method, which uses 3 low dynamic range images and events, outperforms all the compared methods in terms of PSNR in the linear and tone mapped domains, and also in terms of the HDR VDP2 image quality metric. Here we present some of our results on the HDM HDR dataset using synthetic event data. Note that in this scene, our method is able to better reconstruct the fast-moving flames of the fire. In this fairground scene, our method is better at recovering and aligning the moving highlights. And now we present some results on the DSEC driving dataset using real event data. In this scene, our method better reconstructs the details on this fast-moving brick wall. And in this scene, our method recovers and aligns the details on this drain cover on the fast-moving road, which all other methods fail to reconstruct well. We perform a number of ablation experiments to validate the effectiveness of each component of our model. We observe that the model performance increases with each additional component. Note that each additional module increases the overall number of network parameters, so for each ablation we balance the overall parameters by increasing the number of parameters in the remaining modules. Still, our complete model configuration performs the best overall, as increasing parameters in the remaining modules leads to overfitting of the model. In conclusion, we have presented an HDR image reconstruction network which combines event data with low dynamic range images. Our model combines the best of both worlds of each input modality by leveraging high frequency and high dynamic range information from an event camera for better alignment in moving regions, and low frequency, low dynamic range images for more accurate color and detail reconstruction. We have introduced a novel event-to-image feature distillation module that transforms event features into the image domain features and exploits higher frequency information provided by the events using a sliding window over the input event stream. Our model outperforms state-of-the-art methods which use only images or only events or events with a single low dynamic range image with better detail reconstruction, particularly in dynamic scenes. Please come and see our poster and visit our project website for more details and results. Thank you.